Hi everyone, welcome to part 2 of our basic factoring series. In this video, we're going to introduce a key technique called factoring by grouping. If you haven't already, go ahead and like and subscribe and we'll get started. To get the most out of this video, for this video to really click, you should already be able to find pairs of factors of whole numbers and to take common factors out of algebraic expressions. If you need a refresher on either, you can check out part 1 of this series first. So in this video, we're going to learn how to factor expressions by grouping and how to apply this grouping technique to factoring quadratic expressions. We're going to stick to integer coefficients again in this video so that the focus is on the techniques and we're not bogged down by decimals and fractions. Okay, let's do some maths. So consider this expression, x cubed plus 6x squared plus 4x plus 24. Suppose we want to factor this thing. Right away, we can see that there are no common factors that apply across all of the terms. Okay, however, if we look at the first two terms, there's this common factor of x squared. If we look at the latter two terms together, there's this common factor of 4. So let's see what happens if we take those common factors that only apply to those smaller groups of terms. Okay, in the first pair, we have x cubed plus 6x squared equals x squared times the quantity x plus 6. That's what we have left over when we factor x squared out. And then we have 4x plus 24 equals 4 times the quantity x plus 6. And we want to notice something here, that both of these groups had a hidden common factor of x plus 6. When we factored those individual groups, it revealed this common factor of x plus 6. Okay, and that is at the heart of why factoring by grouping works. That's why it is a technique that we're even talking about, because in this case, when there's no obvious common factor initially, but by factoring the individual groups, a common factor reveals itself, that is actually fairly common, and so it's worth talking about. So let's see how that idea helps us factor the entire expression. So here's the original expression, just rewritten. And this is going to be more how we typically write this on paper. Okay, so first we want to rewrite the first and second pair of terms. Okay, so those are the factorizations we saw on the last slide, but now we're adding them together because it's replacing the entire original expression. Okay, now we use the fact that there's this common factor of x plus 6, so we factor that out, and what we have left in the first term is x squared, and in the second term is plus 4. Okay, so now we have the factored form of the original expression. If we need to, we can summarize that with a single equation. X cubed plus 6x squared plus 4x plus 24 equals the quantity x plus 6 times the quantity x squared plus 4. And that's factoring by grouping. So that's a pretty typical example, and we want to know that it should be the next thing we consider once we've already considered common factors. Okay, we should always scan first for common factors. When we see that there are no common factors, the next thing to scan for is whether factoring by grouping is potentially going to play out. Okay, so let's see how this same technique applies to quadratic expressions. We're going to first review what we mean when we talk about quadratics. Okay, so a quadratic expression, for now we're just dealing with one variable at a time, say x, is any expression that we can write as a times x squared plus b times x plus c. Okay, and here these coefficients, a, b, and c, are all constants, as opposed to x, which is a variable. Okay, further, we can call a the leading coefficient because it goes with the x squared term, b the coefficient of the linear term, okay, linear because in that term x is only to the first power, and c we can call the constant term. I want to point out something about this quadratic expression compared to our example we just saw. This quadratic form only has 3 terms, but part of the reason the factoring by grouping worked in the last example was that we had an even number of terms. In that case, we had 4. And so it's less obvious, I would say, in this case, that factoring by grouping would even be relevant. And so it's sort of a trick that we can use to factor things like this in a systematic way. So let's see what I mean. Okay, so say we want to factor x squared minus 2x minus 63. The first step is going to be to find a pair of magic numbers whose product matches the product of the leading coefficient times the constant term. In this case, that's going to be 1 times negative 63, or just negative 63. And then the same two magic numbers should add together to give us the coefficient of the linear term, which in this case is negative 2. So the way to do this efficiently is to get good at running through pairs of factors of the number where you need the product. So in this case, the negative 63. So we want to run through pairs of negative 63, and then as we come up with a new pair, we just do a quick check. Does the sum equal negative 2 or not? Okay, now there's another trick we can use here looking at the signs of these things. If we want the product to be negative, that means that one of the magic numbers is positive and the other one's negative, so that the product will be negative. Right? A positive number times a negative number is negative. And then the fact that the sum is also negative tells us that the factor that gets the minus sign, the factor that's negative, should be the one with the larger magnitude. So with that in mind, let's go ahead and run through pairs of factors of 63. We can do 1 and negative 63. Okay, but they're too far apart. If we add these together, it's nowhere near negative 2. Okay, so we need another pair. What about 3 and negative 21? Again, too far apart. The sum is going to be much greater in magnitude than 2. So those two don't work either. What about 7 and negative 9? Well, these two, again, multiply to negative 63, but they also add to negative 2. So these are the magic numbers that we needed. This is the pair we were looking for. Great! What do we do with that? So what we do is we use those magic numbers to rewrite the original middle term, okay? So a linear term. So in this case, we had negative 2x as our linear term. We're going to replace negative 2x with plus 7x minus 9x, where the positive 7 and the negative 9 were exactly the magic numbers we just found. Okay, and now in this form, this thing is susceptible to factoring by grouping. Okay, so let's see what that looks like from start to finish. This is just a reminder that we found that we want to rewrite negative 2x this way as 7x minus 9x. Okay, so there's the first step. Now let's look at the first pair of terms, x squared plus 7x. There's a common factor there of x. In the next pair of terms, negative 9x minus 63, there's a common factor of 9. It's actually more convenient to take the negative out with it. Okay, so we're going to factor out a negative 9. And this is what we should get. From the first pair, we get x times the quantity x plus 7. From the second pair, we get negative 9 times the quantity x plus 7. And lo and behold, now this common factor of x plus 7 has revealed itself. Okay, and so let's factor that x plus 7 out. Left over in the first term, there's just a factor of x. In the second term, there's a factor of minus 9. And so our factored form of x squared minus 2x minus 63 is the quantity x plus 7 times the quantity x minus 9. Now, before we move on, I just want to point something out. Some of you may know this already, and some of you may have picked up on this, but there is a shortcut that's sort of hiding in the background here. Notice that both of these factors, x plus 7, x minus 9, are obtained by taking the variable x and just adding the magic numbers. Our magic numbers were positive 7 and negative 9. And so can we just skip to this every single time? Well, so partially that depends on your teacher and what kind of work you need to show. But in this case, yes, mathematically speaking, in this case, yes. And that's because the leading coefficient was 1. And that's an important factor here. Factor. That's an important fact here, that the leading coefficient is 1. If the leading coefficient were something other than 1, it wouldn't be enough to just add the magic numbers to the variable x. Okay, and so we'll see examples where this wouldn't work a little later in the video, but when the leading coefficient is 1, you're dealing with a quadratic, you found these magic numbers, it will always work out that the factorization is going to be x plus the first magic number in parentheses times x plus the second magic number in parentheses. Awesome, so let's summarize this technique. If we want to factor a quadratic by grouping, it's only going to work if these magic numbers exist. Okay, so we have to be able to identify magic numbers u and v where the product of the magic numbers matches the product of the leading coefficient with the constant term, and the sum of the magic numbers matches the coefficient of the linear term. As long as those magic numbers exist, you can use this grouping approach for your quadratic. Okay, so we use the magic numbers to expand the middle term. So if the magic numbers are u and v, it'll look like this. We replace plus bx with plus ux plus vx. And at that point, as long as we've chosen the correct magic numbers, this form on the right is susceptible to factoring by grouping. All right, so that's the technique. Now that we have seen a few examples, different kinds of examples of factoring by grouping, let's do some exercises. Okay, and here, if you want, you can pause the video and go ahead and try these out on your own. Okay, and if you get stuck, you can check in on the solutions, or otherwise you can just see how you did once you get through them independently. If you're not quite there yet, totally fine. Go ahead and follow along with me. All right, either way is great. So, part A, 3x cubed minus 6x squared plus 4x minus 8. We want to bring our attention to the first pair of terms, see if there's a common factor there. Okay, in this case, we can pull out 3x squared. When we do, we're left with the quantity x minus 2. So since that one did factor, we can look at the second pair of terms and ask the same question. In this case, there's a common factor of 4. If we take a 4 out of both terms, we're left with the quantity x minus 2, which is good because that means the grouping worked. Grouping worked because this common factor of x minus 2 has revealed itself. Okay, so we'll factor the x minus 2 out next. In the first term, we're left with 3x squared. In the second term, we're left with plus 4. And so it turns out that if we're only dealing with integers, and really if we're only dealing with real numbers, this is as far as we can factor. Okay, in a later video, maybe we'll revisit this 3x squared plus 4 and see if there's anything we can do with it. But this is where we'll stop for now. All right, so this one's factored. Great. Next up, t squared minus 13t plus 42. Okay, so here's one of our quadratic examples, and I want to show you one way that you can write this out on paper, one way that you can show your work in a kind of scratch work format before you start writing out your formal response. And so this isn't the only way to do it, and this isn't how I learned it when I first learned this technique, but I do think it's helpful. So we make this kind of space somewhere in our paper, and we put some kind of multiplication sign in this top corner and a addition sign in the bottom corner here. And again, we need to remind ourselves of our goal. And so what we're trying to do is find a pair of numbers, and the pair of numbers are going to go on, each number is going to go on either the left or the right of this figure. Okay, and so we need a pair of numbers whose product is equal to the product of the leading coefficient with the constant. In this case, the leading coefficient is 1 and the constant is 42. So we need product of 42. And we need the sum to match the linear coefficient, which in this case is negative 13. And so this sort of summarizes what the magic numbers need to achieve. Again, we can use the signs to our advantage. The fact that the product should be positive means that the signs of the magic numbers should match, either both positive or both negative. Then the fact that the sum is negative means that between the two, the only possibility is both negative, right? We need to add, or if we add two positive numbers together, we're going to get a positive sum. So we're looking for two negative numbers that multiply to 42 and add to negative 13. All right, so there's negative 1 and negative 42. The sum is going to be too big. What about negative 2 and negative 21? Okay, the sum is negative 23, still too large of a magnitude. What about negative 3 and negative 14? Okay, sum is going to be negative 17. We're getting closer, but it's still not quite there. What about negative 6 and negative 7? I think these are the ones. So negative 6 times negative 7 is positive 42, and then negative 6 plus negative 7 is negative 13. And by the way, here you can kind of see why this form is helpful. It just kind of summarizes everything in a compact way on your paper. You sort of do an arc. You read it like an arc across the top from negative 6 to negative 7 with the multiplication sign in the middle to give you the product above, and then you sort of read it across the lower arc, negative 6 plus negative 7, to get the sum, negative 13 below. Okay, so we found the magic numbers. What are we going to do with these? We're going to use them to split the middle term. Instead of negative 13t, we want to write it as negative 6t minus 7t. And then factor that form by grouping. And so looking at the first two terms, t squared minus 6t, there's a common factor of t. And then when we pull that out, we're left with quantity t minus 6. As long as we've chosen the magic numbers correctly, this will play out. Looking at the second pair, there's a common factor of 7. In fact, it's even more convenient to pull out a negative 7. When we do that, we're left with the quantity t minus 6. Great! Factoring by grouping is working. How do we know? Because this new common factor of t minus 6 revealed itself. So we pull out the t minus 6. When we do that in the first term, we're left with t. In the second term, we're left with negative 7. And so we've factored the original quadratic. And again, we can take another look at this and notice that the shortcut would have worked here. The shortcut I mentioned before would have worked because, again, the leading coefficient was only 1. So it would have worked to write the factors as t plus the first magic number times t plus the second magic number. We would have gotten exactly the same thing. Okay, it's good to understand the factoring by grouping because, again, it's a systematic approach that works regardless of whether the leading coefficient is 1. Speaking of which, let's see an example where it's not. Okay, here's 2u squared minus u minus 1. And if you did catch part 1 of the series, we're going to encounter one of the examples from that video along the way. Okay, so we need to find our magic numbers. The product should match the product of the leading coefficient and the constant. Leading coefficient in this case is 2, and the constant is negative 1, so we want a product of negative 2. And the sum of the magic numbers should match the linear coefficient, which in this case is negative 1. And looking at the signs, it seems like we want the magic numbers to have opposite signs because the product should be negative, and it seems like the larger of the two factors should be negative so that the sum is negative. Okay, so if we're thinking of factors of negative 2, notice positive 2 and negative 1 doesn't match those conditions, and so this isn't going to work, and we can check that very quickly here. 2 times negative 1 is the right product, negative 2, but 2 minus 1 is positive 1, not negative 1, and so that doesn't work. What if we switch the signs? Negative 2 times positive 1 is still negative 2, but negative 2 plus 1 is indeed negative 1, so these are the magic numbers that we needed. And what are we going to do with those magic numbers? We are going to split the middle term from negative u to negative 2u plus u, where again the coefficients on negative 2u and plus u are exactly the magic numbers we found. We're going to factor by grouping, starting with the first pair. There's a common factor of 2u. When we take the 2u out, we're left with quantity u minus 1. Looking at the next two, there's no obvious common factor there. There is the trivial common factor of 1, and it can be helpful in this case to write that factor of 1 on the outside, although it's not absolutely necessary. I would say at minimum, if you want some visual alignment, you can put parentheses around the u minus 1 at least, even if you don't write the 1 in front. And then you have the example from the last video. All right, so looking at this thing now, there is a common factor of u minus 1 that revealed itself. So we're going to factor that out. In the first term, we are left with 2u. And in the second term, we're left with plus 1. And this is where writing the 1 explicitly in front can be helpful, although it's not mathematically required for correctness in our work. Okay, you definitely need it here at the end. Okay, so we should have 2u squared minus u minus 1 equals quantity u minus 1 times the quantity 2u plus 1. And notice that if we tried to use the shortcut we saw before, where you just add the magic numbers to the variable to create your factors, that wouldn't have worked here. Okay, that would have given us factors u minus 2 and u plus 1, and neither of those are factors of our original quadratic in this case. And so it's very important if you're going to use that shortcut, which is, I would say, widely advertised, it's only valid as long as the leading coefficient is what number? 1 only, okay? As long as the leading coefficient is 1. Great work, everybody. Let's wrap up here. So, what did we learn in this video? We learned that if there are no common factors across all terms, then we should check among groups of terms. If, in the process of looking at these groups, a new common factor is revealed, then the grouping worked, and factoring by grouping as a technique will work to factor your expression. Okay, that's true in general with factoring by grouping. Specifically, if you want to factor a quadratic, ax squared plus bx plus c, then you need to find a pair of magic numbers such that the product of the magic numbers equals the product of the leading coefficient and the constant term, and the sum of the magic numbers equals the coefficient of the linear term. All right, great work again, everybody. If you learned anything new at all, go ahead and like and subscribe. I hope this one was helpful. We got more basic factoring techniques on the way in this series. But go ahead and let me know in the comments if anything was confusing at all, if you have any questions, or if there are other topics that you'd like to see covered in our channel. All right, everybody, thanks again. Catch you next time. Cheers.